So this video is going to show you a geometric use of the cross product. So the cross product can also be used, and apart from the things that we've discussed in class, it can find areas and volumes for you. So if we have a parallelogram that lies in two-dimensional space, so for example, if we have a parallelogram, let me draw one out for you here. And let's say what the size of the parallelogram look like. So let's say this corner is the origin, 0, 0. Let's say that this corner is 2, 0. And this corner is 3, 4. And so then this corner must be 5, 4. So I can ask you, what is the area of this parallelogram? So note that for this parallelogram, we could think of this as being spanned, the parallelogram that comes from the span of, well, maybe span is a word I shouldn't be using here, but it kind of comes from these two vectors that, let me call this u and v here. So these two vectors are going to determine the parallelogram, because we could translate u up here, we could translate v over here. So we have u is the vector 2, 0. And v is the vector 3, 4. Now, as it turns out, we can take the cross product of these vectors to find the area. I'll show you how to do it. But cross product is something you're only allowed to do for vectors that live in R3. So really, we're going to think of these two vectors as living in three-dimensional space, and we're just going to tack on a z-coordinate that's going to be 0. So really we're thinking of u as 2, 0, 0, and we're thinking of v as 3, 4, 0. There's no problem with us adding an extra z-axis that's going out of the page and coming into the page and stuff like that. So that's what we can do. So if we make those changes then, as it turns out, the area of this parallelogram is simply given by the magnitude of the cross product. So to find the area of this parallelogram, all we have to do is do 2, 0, 0 crossed with 3, 4, 0. When we crunch that out, 2, 0, 0, 3, 4, 0. I'll skip the steps here, but you'll see that you get 0 and 0 and 8. You can check for yourself that that's correct. So the area is equal to the magnitude of this 0, 0, 8 vector, which is the square root of 0 squared plus 0 squared plus 8 squared. So the area is just 8. So the area of this parallelogram over here is equal to 8. So that's a nice little geometric use of the cross product. I should say that it doesn't have to be vectors, parallelograms that live in the in R2 in the plane. That if we were to set up some axes here, so x, y, and z, and I were to just draw two vectors here at random, like here is some vector u, and here is some vector v, and we translate here, and so we get some overall parallelogram there. The same thing happens, that, let's say u here, I'm just going to make something up, is going to be 4, 4, 1, and let's say v is equal to 1, 3, 3 here. Then the area of this parallelogram that's flowing around three-dimensional space is just the same thing, is equal to the magnitude of u cross v. So I'll skip computing that in the interest of time. You can do that by yourself. Sometimes you'll see something about triangles with this, with these kind of problems. So let me show a problem I just kind of make up on the spot here. So let me give you 3 different points lying around here in 3-dimensional space. X, Y, Z. I'm just going to make this up on the fly. Let's say that this point here is 1, 1, 1. Let's say that this point here is going to be 0, 4, 4. And let's say that this point here is going to be 3, 5, 0. And so we have these 3 points floating around in 3-dimensional space. We could form this triangle here, and the question is, what is the area of this triangle? So the nice thing about triangles, maybe you can see where I'm going to go with this, but a triangle is simply going to be half of a parallelogram. So if instead of drawing this just as a triangle, if we could find the entire parallelogram here, we can just find half of the parallelogram, find the area of the parallelogram, take half of it, and we'll be done. So how do we do that? Well, we need to figure out what this vector is. We need to figure out what this vector is. So u and v. We take the cross product of those 2 vectors. We find the magnitude of that cross product. That'll give us the area of this parallelogram over here, and half of that will give us the area. So for the area of the we have to compute the 2 vectors here first. So we're going from 1, 1, 1 to 3, 5, 0. So that would be 3 minus 1 is 2, 5 minus 1 is 4, 0 minus 1 is minus 1. V, so going from 1, 1, 1 to 0, 4, 4, would be minus 1, and 4 minus 1 is 3, and 4 minus 1 is 3. So we're looking for the cross product of u and v here, I hat, j hat, k hat. So 2, 4, minus 1, 3, 3. And so crunching this out, hopefully I won't make any mistakes here. I see I have 12 minus 3 is going to be plus 15. And then I'm going to have, I think we're going to end up with plus j minus 6j is going to be minus 5j. And then plus 6k plus 4k is 10k. So I was doing that without writing down stuff. You should be writing down stuff, but it's always good for me to think about how I can check my work. So maybe I can come over here to check my work. So recall that the cross product needs to be orthogonal with the original vectors. So if I do 2, 4, minus 1, dotted with 15, minus 5, and 10, well, I end up with 30 minus 20 minus 10 is in fact 0. So hooray, that checked out. Check for yourself that when you do v dotted with u cross v that you also get 0. So hooray, we have found the cross product. So the area of the parallelogram is equal to the magnitude of this. So 15 squared plus minus 5 squared plus 10 squared, which is going to be square root of 225 plus 25 plus 100. And so that is going to be square root of 350. And so the area of the triangle, what we were trying to find up here, is 1/2 square root 350. So 1/2 square root 350. Okay, so there's one last problem type that we can do here, and that is parallelepipeds. So this is a three-dimensional specific thing, but basically now instead of having two vectors form a parallelogram, but we can have three vectors form a kind of tilted prism in some way, a parallelepiped. So let's say we have vectors u, v, and w. So there's a base. Let's see here. Going to go up there, there. It probably could be neither than that, but some three-dimensional box. Think of a cube or a rectangular prism, but just kind of shifted in some way, a little bit off center. Take a deck of cards and tilt it a little bit. So as it turns out here, the volume, so instead of computing area of a two-dimensional shape, we're computing volume of a three-dimensional shape. The volume ends up being, there's two ways that you can express this. You can say it's the dot product of u with v cross w, and that might be negative. Dot products might be negative, so we want to take the absolute value of the whole thing. Or, and I should say you can interchange the order there, and things would be okay. This is equivalent to doing the determinant of the 3x3 matrix, where you just list out the entries of u and then v and then w, and then compute that determinant. And then so you get a scalar in that case, and then you take the absolute value of that scalar. So if we were to make up, just make up numbers here, u is 1, 0, 0. This clearly isn't matching the picture. That's okay. V is 1, 2, 3. And w is going to be 0, 2, 1. Then the volume of the parallelepiped, this is a word I'm working with notes that are just off screen a little bit. I have to check them to make sure I'm spelling that right. It's simply, well, we want to have the determinant of 1, 0, 0, 1, 2, 3, 0, 2, 1. So find that determinant and take the absolute value of that at the end. So if you compute the determinant, I'm going to skip the steps in computing the determinant. It would be good for you to check this yourself. The determinant ends up being here -4. And so we don't want to have a negative volume. So the volume here ends up being 4. And so that's how you use cross products to find areas and volumes.